Hi everyone. In this video I'm going to be talking about what it is we can do when we're interested in inference for two populations. So to this point in class we were learning how to perform inference using a single sample from a single population. We saw how to draw a sample and build a confidence interval in a way that would mean, for instance, 95% of similarly constructed intervals would contain the population mean. We saw how we could test hypotheses using the rejection region approach and the p-value approach. But sometimes it's the case that we're going to want to compare two populations. In fact, one of the things we might want to do is to be able to compare the difference of means between the populations. So this is particularly useful if we're interested in testing the effect of some treatment against some baseline control group. But there's other reasons why we might wish to compare means. And anyway, we can think about using the difference of means, the difference of sample means, as an estimator for that difference of true population means that we're really interested in learning something about. So in order to see how this can be done, I'll first talk about the sampling distribution of the difference of means so we know how we'll be able to proceed with inference. So suppose we have two populations and we're assuming they're independent and symmetric, hopefully normal, although the central limit theorem tells us that this won't be a strict requirement. What we can do is we can select a sample of size 1 or size n1 from one population and a sample of size n2, for instance, from the other, and using these two samples we can compute the respective sample means. Now we can subtract the two means and that'll give us our estimate of the difference of the population means. And in principle we could then compute the difference in sample means for all possible pairs of samples, though we wouldn't actually really need to do this. If we did, it would provide us with the sampling distribution of the difference of the sample means. Now in reality, all we really need is to have one set of samples, one from each population, and then one difference in sample means. And we know that regardless, this statistics, this difference of the sample means that we would have computed, would have come from that larger sampling distribution of the difference in sampling means, though we need not compute all those possible different sample means, differences of sample means. Like any sampling distribution, the sampling distribution of the difference of sampling means has as its mean the population parameter. This means that in this case, the expected value of the sampling distribution of the difference of means is just the difference of population means. So for instance, the expected value of x bar 1 minus x bar 2 is just mu 1 minus mu 2. So that's pretty predictable, right? What about the standard error of the sampling distribution of the difference of sampling means? Well, it's a bit more complex. As it turns out, and as you might expect, the justification is a bit more theoretically complex than we really ought to concern ourselves with here. Basic idea is based on a difference of variances rule. The variance of the sample differences, the variance of the sample differences of variance is equal to the sum of the sample variances. So we need to take into consideration the sample sizes, though, and the standard error we actually write down is the standard deviation of the difference of sample means is equal to the square root of the sum of each variance divided by each sample size. Alright, so at this point it's best just for me to remark that you ought simply observe that depending on our sampling distribution we get a different standard error. And there's a whole bunch that we'll see. You're not responsible for all of them, and you'll never actually be computing these yourself anyway in practice. You'll have statistical software for that, though it's a good idea to know where they're coming from and what they are. I'll provide these to you on the exam to the extent that you'll need them, and you'll essentially just need to know how they're used. Alright, so finally, assuming that populations are large or that we have a sufficiently big sample such that the central limit theorem applies, then we know the sampling distribution will be approximately normal. That lets us do a whole bunch of neat things. So for instance, if we assume that the sampling distribution is normal, we're able to build a z-statistic. That's this right here. It's pretty familiar. It's just the difference of sample means minus the difference of population means divided by the standard error that I introduced on the preceding slide. And well, if you're using the z-statistic, we're standardizing, and therefore we can use the standard normal distribution with mean 0 and standard deviation 1, and that'll help us with inference. So here's an example. Suppose we care about the heights of boys and girls in Pittsburgh. We have a sample of 13 girls and 10 boys. We know something about the population distribution of heights. Girls are taller and have a narrower distribution than boys. So for instance, the mean for girls is 56.4 with a standard deviation of 2.7, and for boys the mean is 55.7 with standard deviation 3.8. Now the difference in sample means is that we'd actually compute would vary depending on which samples we actually obtain, but we do know that the difference in we do know that the difference in population means is going to be 0.7. So what I'm doing here is a little bit backwards. Usually we're trying to learn about the population from the sample, not the other way around. But there's a reason for this, which comes on the next slide. We can find the variance of our sampling distribution just using the standard error from the previous slide. It's 2.005, and of course we're actually going to want to take the square root of that because what we're interested in is not ultimately the variance but the standard deviation. So that's going to be 1.416. So now I'll show you the probability of finding that girls are taller than boys in our sample, which we never bothered to draw, but presumably could. It's just the probability, the difference of the sample means greater than 0.07 divided by the standard error of the sampling distribution of the difference of means, and that's 1.416. So what's the point of doing this? Well, one point is to show how to use the z statistic here for the difference of sample means. The other point is to point out that this probability we've actually computed here is really small. So what's going on here? Well, we know the population mean of girls is higher, but with small samples the probability of getting that the sample mean for girls is higher than the sample mean for boys is less than 70%. What's going on here is this is illustrating the fact that even though we've got this known difference in the population, we need large samples in order to be able to identify the effects of small differences, such as this small difference of less than an inch between the average heights of girls and boys in the population.